Varun Mohan is a CH graduate, currently pursuing his MTech EC Embedded Systems at National Institute of Electronics and Information Technology. He's interested in RTL design and building systems and accelerators with FPGA. He's also very keen about bare metal C programming, hardware software co-design, and computer architecture. Over to you, Varun, to go ahead with the presentation.
Hello.
Yes, Varun, you're
Hello.
audible.
Am I? Yeah. Good evening, everyone. I'll just share my screen. Are you able to see my screen?
Yes, it's
Okay. Yeah. So welcome to this presentation. Actually, in fact, I don't have any presentation. I'll just have a quick demo on how you can get quickly working with microwatt on and against FPGA. So I think by now you should be familiar with what microwatt is. It's an open core which implements the now open power ISA. I believe it is the ISA 3.0 ISA. So the original repo is this one, written by Andrew Blanchard. It is written for a FPGA development board from Digilin called the RT A700T. So it has a lot of peripherals like it has an Arctic 7 FPGA with Ethernet, DDR, SPI5, etc. So this is the original product, original repo. What I have done is I have stripped it down to a very basic system, which just has some VRAM for its storing its code and data and a GPIO. So it can be a good starting point for students like you, if you want to get, don't have to go through all this, getting limited by this all the code in the original repo. So before going into the code itself, I'll just quickly show you the architecture of currently how the SoC is being implemented. So basically, you have your microwatt core here. Out of the core comes two buses, the instruction bus and data bus. Both of them are based on the wishbone bus architecture. And currently, since you have two masters, we need a bus arbiter to, either only one of the bus should have, one of the, like either I bus or D bus should have control of the bus. So we have a bus arbiter there. And again, out comes a single wishbone 64 bus. And now after that, basically you have an address recorder, and there are two sets. There are two sets of what do you call peripherals. You can say one for 64, one that can work with 64-bit data line, another set which is like the one shown below this blue line usually is designed to work with 32 bits of data. And address lines are all implemented to be 32-bit in both the cases. So here in the top, you can see there is you have this address recorder. So basically in the 64-bit data lines, you currently I only implement the VRAM, which stores your code and your data, basically your C program or whatever you want to run on the on your microwatt core. And you have this so yeah, so you can see the addresses here. Anything starting with 00 out of the 30 bits, first two bits are 0 means it goes to the VRAM. If it is 11, it is redirected to the slave IO, which then goes to your data converter, which converts from 64 to 32 bit, and your other slave IO. So the address decoder actually controls like you have a here as I already told you, you have a single bus. So all the master output lines or the output from the CPU can be connected individually to connected to all the peripherals equally, because only the master is driving. But in case of the output lines from slaves, you can see that data and control lines, they have to be merged because they cannot drive a single bus together. So we have a mux, and again the mux selection line is based on the address decoder. So basically, if the address is 00, it will select this line. It will be this path. If it is starting with 11, basically it will select this. So the address is 11. This will be selected from the input from the mux. So that is how the address decoding and how multiple slaves can be connected on a single shared master, single shared bus. Similarly, if you come to the bottom part, you have the 32-bit peripherals. Then again, you have the similar address decoder. And here, all your addresses start with 11 because that is the case what we are written here. Anything starting with 11 should come, will be passed here and will come to this way, to this bottom section. And from there, again, the other bits of the address is checked to again do the same thing what we did here. So based on the address, the output of either from one of the slaves is selected and passed back to the processor. So for using as the slave select line, what the SOC uses is there is an wishbone CYC signal. So based on that address, it passes the CYC signal from the processor either to this or this based on the address. So that is how it selects that individual slaves. So that is the basic architecture. So uh, how the SOC is designed. So you have the core, you have the shown arbiter, which select either the IBus or DBus to control over the shared single wishbone bus which comes out of the arbiter. And then you have these address decoders, which basically selects which slaves has access to the bus, like based on the individual addresses of the peripherals. Let's have a quick look at the code. So this is the repo which I have created. I will share the. So you can simply clone this and directly load it, this in Vivado. You can open this microwatt SOC minimal.xpr file, and it should open something like this. And here, these are the source files. So if you open this SOC file, you can actually see the this is the address decoder implementation. Like you can see the uh, address is basically this. So here it is whatever I have shown here, the bottom part, this bottom part. So the first two bits will be obliged one because that is how the top decoder is implemented. So in the rest, the other bits are verified to understand like to decode slave which slave which are we trying to address. So I have added some command like add here. Add here you can see where like if you want to add a new wishbone peripheral, you can simply add it. You can search for this add here in the source code, and then that you can add the individual signals and the code depending upon the type of peripheral that you're adding. I'll give a demo on that also. So this is a basic implementation uh, on the VHDL or the digital design side. So yeah, you should have some understanding of digital design and VHDL to read through this and understand how this is, everything is connected together. And once you are done with this, so basically you can generate the bitstream. But before that, what you have the SOC, you have everything in everything, but we need the software to run on the FPGA as well, right? On the core as well, right? So that is a separate flow. So when you download the repo, you will have this uh, software directory, which which I have adapted from, I think, the Hello World project in the original repo. So basically, this is a makefile based implementation of your C. So this is your main user file, which you can like for writing programs for the core, you just need to worry about the main.c. You can write program whatever programs you want in the main file. Other things, this is the startup script, which for understanding, I think you should have a fair idea about the power ISA instruction set, because this is written in assembly. But for writing programs and get things running on that, you don't need to worry about that. You can simply replace the main file here, main code here. And for adding additional source file, you can add it. You can simply go through the what do you call the make file and adapt it for multiple source file as well. So once you have uh, so this is like, again, if you're familiar with how microcontrollers work, this is the same thing. Memory mapped access to the different peripherals. So if you can see, this C0007 is what exactly we have mentioned here. So we are basically saying that we want to have access to this display peripheral. So we are giving this address. So this is basic stuff. You define a structure and a pointer to that, and each individual registers you can then access using this arrow notation. So that is basic C. And once you know the base address of your device, you can define a structure like this and individually access the registers. So basically, what the peripheral is a slave GPIO. So basically, your general purpose output, which I have connected to the onboard LEDs. So there are 4 LEDs on the board. I don't know this notification. This LED 0, 1, 2, and 3. So I connected to that, and in the code, we are actually setting the 4 bits as output and then driving them in some particular pattern. So if you program this and load into the FPGA, we could see this pattern running. And now once you written and made changes to this program, what you can do is simply run make open, combine and it will generate the firmware.hex file. So this is automatically referred in the VMS. So what I'm doing is, once this is generated, it is copying the firmware file to the source directory in vmodel. It could be better ways of doing this, but idea is, I think Lucas mentioned this in his presentation. Here we have the FPGA design and we have the ELF file. So that there should be some way to for us to upload the ELF into the FPGA memory. So what currently we are doing is that using Verilog and VHDL, we can initialize our RAM structures using a hex file. So it during synthesis, it will read the content from this schema.hex file, and it will be used to initialize your VRAM contents, and it is part of the bitstream. So basically, your ELF become part of your bitstream, and you can simply load the bitstream to FPGA, and the VRAM will have that ELF automatically, and the core can start working on that, executing the ELF. Not the ELF, ELF, you have to convert the ELF to binary and then to plain hex format. That is already taken care by the makefile. You can go through the makefile, and it is not very complicated. With a few commands. There is a Python script. Everything has been adapted from the original, the Hello World repo in, written by Anton Blanchard. Yeah, once you have made your changes and you have compiled your program, what you have to do is you have to reset synthesis so that uh, the synthesis of your basically you should reset only synthesis of your what do you call it, DRAM. I have not figured out a way how to do that. Currently, I'm resetting the entire project, and so what it does is it synthesizes everything again. And as I mentioned, the firmware is loaded or is part into the DRAM initialization as part of the synthesis process. So it will the firmware.hex will be read again, and it will be the new whatever the new hex file you have generated will be part of the bitstream. So you can simply do a generate bitstream, and it will do one by one the steps like optimization, synthesis optimization, placement, and routing. Meanwhile, it does this. I will show you how to add. If you want to add your own course, how to do that. Not code, I mean a peripheral, a Wishbone peripheral. So, as I already mentioned, I have marked this add here signal. Everywhere where when you are adding it, uh, when you're adding a new peripheral, where you might have to edit the code. So you can simply search for this. It depends. Some places you may not have to add this. It depends. So let's go from here. So first one is here. I'm actually using a GPIO for. So this is another GPIO for which I disabled for free on GitHub. So you can download this and use it. So it is implemented in our Verilog, and it would work because Vivara does support a mixed language synthesis and synthesis. So what you have to do is the source file which you get downloaded from here, you have to add it as source files in your design, and then you can instantiate your GPU or whatever IP code and your the associate.html file here. And so then you have to, if you see the connections, VHDL do supports what are called records, something like structs in C, where you can group to multiple signals or multiple types together. So Wishbone has been implemented as records in here. So the original bus from the CPU, etc., is using the same record, format. So most probably the code that you're going to download will have individual Wishbone buses, bus signals like the clock, address, data, etc. And so when you're connecting, you cannot simply do this stuff. This could have been much easier, but yeah, you have to individually wire like wishbone address I2 with GPIO in address like that. You have to do that. And any external signals that your GPIO is using, you have to wire that as well. Some you might not be connecting, you can declare them as open, etc. So these two signals, GPIO in and GPIO out, you have to define it. Yeah. Okay, let's go one by one. So here you can see I've defined that open GPIO two signals. One is a master out and slave out. So basically, master out will be same as slave input, and slave out will be the same as master input. And so these two signals are added here. Next, this is used by your your address decoder. So I have added one this thing here, slave IO open GPIO. Then here, yeah, this one. So you are adding a new address space or address section of address and mapping it to your slave IO open GPIO. So we already have 00. This is for your syscon, this is for your original GPIO which came with the project, and I've added open GPIO to be at 0, C0008. Okay. Then you have to connect to your input signals, so directly, which is this GPIO input. And next is, yeah, the output. Okay. The output from the slave should be directed back to the core input based on the address line selection. So that is what we are doing. So when that is done, your core should be part of the bus, and it should be ready for communicating. Like the CPU should be able to communicate with that bus using this particular address. That is 11C, sorry, C008, C0008. Then if your external signals, like in our case, we are using a GPIO, so you have this pins like input, output, and the price side control pins that you have to drive out of the SOC like this. And in the top RT, you take it out from the SOC instantiation and use it to drive some pins on the FPGA board. So here I am using and driving the original GPIO is driving the four LEDs, and the new GPIO which I am added as driving the green color of. There are four RGB LEDs. We are driving the green color on those LEDs. So the other thing has finished. Once you have generated the bit stream, I can develop open hardware manager. I'll show you. So if we can see, you can see this four LEDs blinking in some particular pattern. So that is what we have coded in our C program. We are addressing that using that particular processor. So that is how you can quickly use microwatt, get started with microwatt in your design. So you can clone that repo and start experimenting. You can easily port it to other FPGAs as well. You might have to FPGA in the sense For silings, you might have to work with the XTC constraint file here. Like if you are on a different board, like how the LEDs and buttons are wired, it might be different. And the other things, it should be fairly easy. Yeah, basic understanding. I think you got how to use search bar here. This command which I have added, and you can compare these two repositories, the original one and the one which I have added an OpenGPIO. So you can figure out what all changes has to be made to like add a new what you call paper to your design and work on that. Now, once you are familiar with this, you can even think of trying to run the original repo, which uses almost all the, I believe all the, it uses DRAM, Ethernet, spare flash, everything on that repo. Yeah, that concludes my my this thing. If you have any doubts, you can ask. Yeah. Hello. If you have any doubts, you can ask. Conversion famous, that I split that out of it. Yeah, correct. Synthesis, yeah, resetting synthesis, it takes a lot of time.
Any questions for Varun team? We have
Thank you, Luke.
yeah, we have Yogendra from CDAC also joined the call. Uh, Yogendra, you have any questions on this implementation?
Yes, I have a question. How much resources did it take of the 100T FPGA? I'm curious to know if it was able to fit into a 35T.
You're able to see the screen, Luke?
Yes.
No?
Yes.
So this.
Only 28% utilization. So actually, it might actually fit into. It might actually fit into a 35T. Oh, that's really good.
I believe I have done it on 35T. In last demo, I think I believe I was doing on the remote lab, which runs I think 35T.
Oh, that's fantastic. Because it's a different a big difference in the cost of that for as an affordable FPGA board.
Yes.
So Varun, I have a question. Can we do the what is the tool you are using here? Vivado, right?
Yeah, this is Vivado.
So is there an open source tool through which we can do this work?
Yeah, of course. I think Luke can comment on that. Luke is working on that.
If I may, yes, there is Symbiflow. You can actually use it. It does install, but the thing that I found is that if you have very large adders over 128-bit, over 95-bit, which in the divide unit of microwatt there is, you must use the -no carry option. You must switch off the carry, the use of the carry 4 block in Symbiflow, and likewise in NextPNR Xilinx, because it's to do with the resources of the way that the FPGA works. If you go above a carry of above about 95 in length, it doesn't work. So, but there are options to switch that off. and then it will actually compile and work. Thank you, Ganesh. And yes, Simpliflow GitHub.io. The other one that I used was NextPNR Xilinx, and that's a free software tool as well. Now, the only thing is that these are experimental, and I was only able to get, I think, 35 megahertz with Simpliflow on the RT-A100T, which is absolutely fine for running the kinds of experiments that you've been doing, Varun. But the moment you try and connect to DDR3 memory, obviously DDR3 memory doesn't run at 35 megahertz. So there's a bit of work there. But for initial exploration, you know, I find it's absolutely fine.
Okay, thank you.
Yeah.
Look. And Varun, can you post your the GitHub location so that people can clone and or whatever
I've already done it, sir. In the
on
beginning of that.
the chat window?
I'll do it again, yeah. Yeah, in the chat window.
Oh yeah.
This is the tier 4.
Yes, Shenki, Joel Shenki has actually got Linux running on the RT A7100T. He has a build root and Linux 5.7 kernel, which was worked on by Ben Herenschmidt. I will try and find the link for that.
Oh, who is that running the Linux? You mean on the microwatt?
Joel Shenki, he's one of the team, the Microwatt team from OzLabs. Let me find the link.
That's interesting, actually. So we should go and try out that. You mean
Sai asked the question, I'm little overwhelmed seeing all the code.
There
That
it is.
yielded you.
Shenki, github.com, boot Linux on Microwatt.
oh, the Shenki? Okay,
Yeah.
nice.
What he does is he gives full instructions, and you actually use the tools to flash the Linux kernel and the build root to the actual quad SPI on the RTA7.
Can't we try this one on our the University of Oregon, the FPGA board, whatever we got it on Silicon system? Oh, this is good. Can't we try this? Can we try this on a University of Oregon system? Will it work?
Maybe yes. If it has a quad SPI, it's a light Fury, isn't it? The FPGA board. So I think it has quad SPI NOR flash on board, so it might actually be possible.
Okay.
But like you said in that mail, there should be some form of some way of interact like for the students to interact with the core, like a UART or something. Or maybe asking them to implement PCIe. I don't know. Maybe to
Varun, Luke, what is the comment actually Varun is making? Making is actually like here. Is it okay to do it with the PCI board kind of FPGA? Because the servers, they don't want to keep it on, I'm not sure, how it is possible for them, in the server room, keeping all those boards connected to the
Yeah,
server.
it's
Because
the
we want to
limited
set up
space.
4 to 5 PCI based FPGA boards there, so that we can give access to all the people and try out and all.
I'm just looking at the diagrams online, and the Light Fury does have some config flash. So it's got DDR3 and some config flash, so it should actually be possible to do. Here's the link to the Light Fury. And there's a nice diagram there which shows it has DDR3, so that's good, and it has config flash, so it has some and that's what you'd be able to upload the Linux kernel and the initial RAM disk, the build root, to that, and then the firmware will go directly into the ARTIX and power up.